Hey everybody, it's Ripley back again. I got an easy one for you guys today. This one's a piece of cake. What we're going to do is we're going to talk really quickly about lengths of arcs or arc lengths of curves. So check it out. You guys are going to dig this. So let's say that I have a function of x, all right? Excuse me. And this function goes from a to b, x of course, x equals a to x equals b. And I want to figure out how long this curve is, all right? Excuse me. Now, technically, convention tells us that we're going to use this little script L to determine an arc length. You can probably figure out why this is helpful. You know, it's helpful in determining distances, etc. There's a million different applications. When we get into 3 space, if I want to figure out the surface area of an object, I can wrap this thing through 360 degrees, things of that nature. However, let's not get too far ahead of ourselves. Let's come up with the equation first. Now, check it out. Do you agree that I can take any 2 points on this guy? I can call this xi, y, or x1, y1, and x2, y2. But it'd be a lot simpler if I simply thought of this as a right triangle. Now, you may say, but Ripley, the curve, it's curvy. Well, yeah, but we'll just simmer down now. I'm going to call this delta x, and I'm going to call this delta y. Okay? And then over here, I'm going to say that the arc length is approximately equal to the square root of delta x squared plus delta y squared, right? Now, again, I agree with you fully that the distance from here to here is not equal to the length of the arc. However, what if we were to take an infinite number of infinitely small little hypotenuses, I don't think that's a word, hypotena, whatever, right? If we were to cram these in between A and B, if only there were a technique, dare I say, a mathematical way to figure that value out. Oh yeah, there's this magical thing called the integral, but I'm getting crazy. All right, just hold on just a sec. Now, I'm going to do something nutty here because you're right, I am going to integrate this. But watch what I do to make my life really simple, because if I just slap an integral sign on this, it's not going to make a whole lot of sense, right? So watch, I'm going to multiply by my good friend, the goofy looking one, which in this case is going to be the square root of delta x squared divided by the square root of delta x squared. Watch what happens. All right, this is going to equal, well, this is going to distribute itself into this, right? So I end up with the square root of delta x squared over delta x squared plus delta y squared. Oh, Ripley, you crafty devil, I see what you're getting ready to do. And then this is going to be times, well, the square root of delta x squared is just delta x. Now, watch what this becomes. This is just the square root of 1 plus delta y over delta x, hey, squared, and then out here is times delta x. So you should be able to see relatively easy that if I shrink these delta, to be able to shrink this down to an itty bitty little teeny tiny arc length, what am I doing to delta x and delta y? I'm making them infinitesimally smaller, which means what? These deltas become d's. So guess what? The actual arc length of the curve would simply be the integral from a to b of the square root of 1 plus dy over dx squared times dx, which is great because remember, when I take an integral, this dx represents the width of the subinterval, which is really what we're doing. We're adding up all these little tiny hypotenae, right? And the width of the basically the thickness, how far over we go before we go up to the curve, is just dx, and we're done. Now, you may say, well, Ripley, what if f of x, if this is y equals f of x, I can just as easily write this thing as x equals f of y, can't I? Right? Same curve. Excuse me. I guess we got to be a little bit careful. This would be an inverse, true, but let's think of this as this same curve as f equals x equals f of y. Now, I'm going to use exactly the same trick, only this time I'm going to multiply through by the square root of delta y squared divided by the square root of delta y squared. Now, this is gone, this is gone, this is gone, so what do we end up with? I can still use equal signs. This turns into, well, you should probably see that what I get is a delta, should be there, I end up with a delta x squared over delta y squared. These delta y's are going to cancel, right? this delta y squared and that delta y squared are going to cancel. We'll get plus 1, and then times delta y. Now, I can't say A to B. I'm going to cheat a little bit. I'm going to call this C, and I'm going to call this D. And you may say, well, Ripley, isn't C equal to f of A, and D is equal to f of B? Well, yeah, but let's not convolute things more than they need to be. The exact same arc length is going to be the integral, the integral from C to D of the square root of dx over dy, right, which is the derivative of x as a function of y squared plus 1. So check it out. Don't forget your dy. All this is the square root of 1 plus the derivative squared with respect to x from a to b. This is the square root of 1 plus the derivative squared with respect to y, right? It's exactly the same thing. Now you may say, well, Ripley, didn't we just learn about, oh, this is going to get confusing. Let's pop over a section because I think this will be more fun anyway. Let's change colors. All right, now I'm going to have my curve, but my curve is going to be a parameterized curve. And this time we're going to say from t equals a to t equals b, because this should make you limp and tremble if I look at this thing and I'm like, wait, is this a function of, oh no, it isn't. Is it a function of what? Ah, crud, it isn't. So you're kind of stuck. So we slap a parameter on it, right? Now, remember, same thing, same exact process. I'm going to take, let's do, just my awful, let's go orange. Same exact process, find a value here, cruise over, cruise up, take the hypotenuse, call this delta x. It's still on the Cartesian plane, so that's x and that's y. Call this delta y. I know that the arc length is approximately equal to delta x squared plus delta y squared, right? So however am I going to be able to figure out the arc length if it's parameterized? We can probably see, maybe, you end up square root of delta t squared over the square root of delta t squared. Nah, and watch what happens. Delta t, nothing cancels now, right? I end up with delta x over delta t squared plus delta y over delta t squared times delta t. You see what we got? So arc length is going to equal the integral from t equals a to t equals b, which are just values, we're not afraid, of the square root of dx over dt, the derivative remember, if I've got a parametric, then I've got an x of t equals and a y of t equals, right? So I take the derivative of this guy with respect to t, square it, add it to the derivative of this guy with respect to t, y with respect to t, square it, and delta t turns into dt. That's pretty darn easy. Let me do one for you real quick. Let's find the arc length of y, let's get rid of that color, that's just awful, of, let's go to good old-fashioned black and go away. Let's do f of x equals square root of x from, what should we do? From, what? Let's go from x equals 1 to x equals 4. Okay? Easy enough? All right, so how's this thing work? What are we going to do? We know that the arc length, this is a function of x. We know what this function looks like. I'll draw it down here. Whoop, looks like that, so we don't have to be afraid. All right, so the arc length is the integral from 1 to 4. Now, we know that dy over dx is exactly the same thing as f prime of x, which is just 1 over 2 root x, right? So I end up with the square root of this guy squared plus 1, which is 1 over 4x. Can you see how I got that? Because 4x plus 1 and then dx, right? Now, I got to warn you, 9 times out of 10, what you're going to have to do is you're going to have to do some sort of substitution. You're going to have to be able to do these by hand. I'm going to cheat, and I'm actually going to steal my little TI SmartView because I don't want to push you. We already know how to do substitutions and use tables and all those. So let's close that out. Let's get rid of that. We know that this is equal to the integral from 1 to 4 of, let's just, because it's going to be, well, I guess I could just do it here, couldn't I? Another way to write this is 1 plus 4x over 4x. And then I can putz around with all kinds of interesting things as far as using techniques of integration. Or I can just throw it in a chart, look at the table, but let's do this guy real quick. I think I'm going to do it from here. So I've got the integral from 1 to 4. Let's go math. Let's go, I think it's 9, isn't it? And we're going to go from 1, enter, what did I do? Oh, dang it. From 1 to, I always forget that. It's the worst. From 1 to 4, and then I throw it in here. Remember, you can always use your calculator to check your work. What did I have? I had 1 divided by, don't forget your parens, otherwise it'll just go 1/4 x. 4x end paren, lots of parentheses, which can be confusing, plus 1, and then we'll throw it into dx, and we'll hit enter. I don't know why there's no x there, but we'll hit enter, see if it yells out. 3.1678, interesting. Okay, now I made a promise. I said that you don't just have to do this as f of x, we could do it as f of y. Do you agree that this function could also be written as x equals y squared? Right? Now our limits, instead of being from 1 to 4, is it relatively obvious that f of 1 is 1 and f of 4 is 2? So we're going from the point 1, comma 1 out here to the point 4, comma 2. Now when I do this, let's change colors just so you can see it. We're dealing with that same length of curve. I better get the same answer. So the way that the formula works is L is equal to the integral from 1 to 2 of the square root of 1 plus, now I need dx over dy, right? Not dy over dx. I know that dx over dy, which is just the derivative, it's the same thing as x prime, is equal to 2y. So I should have 1 plus 4y squared dy. I better get the same answer. Well, let's pop back over to our TI. And I'm going to go, let's see, math, and I'm going to go 9, and I'm going from 1, and then don't forget your toggle, to 2 of second square root, what'd I say, 1, second, good Lord. Sorry, ladies and gentlemen, I'm blowing it today. Square root, try this, of 1, I got it, 1 plus. Now, this thing doesn't run on y's, it runs on x's. Hopefully you can see that it makes no difference as far as 4x squared, right? And get rid of that darn 2. Darn tootin' 2, that's terrible. And then we'll slap a dx in here, dx, and we'll hit enter. Go to, it's going to be angry at me for that. Delete, go away. Okay, now hit enter. Look at that, I get the same answer, just like I knew that I would. Now, it would be stupid of me to parameterize this, because I would just let x equal t and y equal t squared. What would I let it be? Y equal the square root of t. Now, you can, might as well do it really quickly. In for pence, in for pound. Remember, this guy is equal to the integral from, now, I start at t equals 1, and I go to t equals 4. Now you may say, wait a second, Ripley, why are you doing that? Well, because x equals t. If x goes from 1 to 4, then t has to go from 1 to 4, right? And this is going to be the square root of, well, dx over dt. Remember, if this is x of t, then dx over dt is equal to 1. dy over dt is equal to 1 over 2 root t. And guess what I end up with? 1 plus 1 over 4t, which is, oh, don't forget your dt, la la la, which is exactly it. It's the same thing. It's easy. It's a piece of cake, all right? And it's so elegant the way it's created. That's my favorite part of this. Other than that, it's pretty formulaic. You're going to have to use techniques of integration. Just remember, particularly in your textbook, if you don't get the little graph or icon, then chances are it means you got to use some sort of analytical technique, like technique of integration, using a table, something like that. All right, thanks for your time and attention. Have an outstanding day, and I will see you tomorrow.